Welcome back, everyone. So in the afternoon, the first talk is given by Zhiyan.
Hi, everyone. In this talk, I'm going to talk about polynomial time preparations of low temperature Gibbs state for 2D Toric code. Basically, we will try to prepare the thermostat using the linked bladder dynamics. This is a joint work with Bo Li, Lin Lin, and Rui Zhang. All three authors are in the audience, so feel free to chat with them. In this talk, I will mainly talk about three different parts. First, motivation, why we care about this problem. Then I will give a quick introduction to 2D Toric code, Davis generator, and the spectral gap. So I guess most of the people are the experts in this area. I will be really quick. Next, I will introduce the main result and the implications of our result. Okay, so start with the motivation. The main problem we care about is the mixing time of linear gradient for low temperature Gibbs state preparation. There are two reasons we care about this problem. The first motivation is if we can prove fast mixing, it often implies efficient state preparation from any initial state. Okay. In the last 2 years, there are some works proposing efficiently implementable linear gradient for general non-commuting Hamiltonian to prepare the thermal state and the ground state. We can prove that these linear gradients can be efficiently implemented on the quantum computer. Here, this beta is the inverse of temperature. T mix is the mixing time of the linear bladder dynamics, and epsilon is the approximation precision to the linear bladder dynamics. Okay. Yeah, according to this result, to ensure that we can efficiently prepare the thermal state or the ground state, we only need to find an upper bound for the mixing time. Basically, we only need to know what is the mixing time. In the literature, there are a lot of works studying the mixing time of linked gradients. Some of them are for the Davis generator. Some of them are for the new linked gradient that was proposed recently. However, most of them focus on the high temperature regime, meaning beta is a very small, or moderate temperature 1D commuting case, meaning beta is order 1. And how the mixing time depends on large beta is not very clear. So here we ask a very natural question: what is the mixing time for large beta, meaning on the low temperature case? Okay. So the second motivation is the faster low temperature mixing might be helpful for passively protected quantum memory. Before introducing the passively protected quantum memory, I first want to introduce the self-correcting quantum memory. Here, we assume that we have a noisy linked bladder dynamics, and we define the linked bladder operator as a noise operator. We assume rho 0 starts from a code space, which encodes some logic information. We also have a decode operator, which will map the density operator back into the code space. Basically, the decode operator can help us obtain logic information from the density operator. Then we say that the system has a self-correcting quantum memory if the logic informations can be almost preserved for a long time, exponentially long specifically. Okay, this is similar to saying the system has a slow mixing time. Okay, however, in real application, self-correcting quantum memory is very rare. One famous example is a 4D Toric code, and we don't know any examples in 3D or 2D. Okay. Now, and this rho t is on the general physical space. Yeah, after you apply the decode operator, it will map rho to the code space. And so you can understand this as a subspace. You will see one example later. Okay.
Also, that should be sup t. Because by t equal to 0, we should definitely be able to decode it.
Yeah. You're right. Sup t. Yeah. It's a typo. Okay. Okay. So now to make the quantum memory more general, we define a new concept called passively protected quantum memory. The idea is in my linked blood dynamics, we add a protection operator. I call it a protector. Then in this new system, we say the quantum memory can be passively protected if along the whole dynamics, the logical information can be almost preserved. Basically, the change of the logical information is exponentially small along the whole dynamics. And this is what we call passively protected quantum memory. We essentially use a protector to protect our quantum memory. Okay. Here we can look at a simple example for the in fact a general example for the stabilizer Hamiltonian. The logical qubits are often encoded in the ground state space of capital H, and we can define the decode operator to be an operator similar to the projection to the ground state space. Okay. Now for the protection operator, we can choose it to be the Davis generator with beta equal to infinity. Basically, this operator itself can help us prepare the ground state. And the goal is to show that the logical information can be almost preserved along the whole dynamics. Okay. So first, we can look at how does the logical information change. Intuitively, there are two steps. We start from the ground state. We apply the noise. The noise operator once. The ground state get excited and change to the low excited state, but with a high probability, the low excited state still has the same or similar logical information as the original state. Then in the second step, we apply the noise operator again. This low excited change to some low prime, which contains different logical information. Intuitively, this is how in the noisy linked Bladian, the logical information changes. Okay. Now, when we have the protection operator, it essentially prohibits the transition in the second step. How to understand this? In this new dynamics, after my ground state get excited, because so when we assume the protection operator has a fast mixing time, this operator will quickly drive the excited state back and keep the original logical information. This is essentially how in the new dynamics, the logical information can be passively protected. Okay. So for example, in Berkeley, people can show that the 2D IC model can be a good passively protected quantum memory for the bit flip noise. Okay. If you also want a phase flip noise, you need to combine the 2D IC model with a 2D photonic cat model. Yeah, I will talk more detail about this later in the talk. Okay. Basically, this is why we care about the mixing time of linked Bladian for low temperature Gibbs state preparation. However, I have to admit, in general, this problem is super hard. And in this paper, we take one step. So basically, we consider the special gap of Davis generator for low temperature 2D Toric code. Okay. One thing I want to emphasize is because 2D Toric code is a local commuting Hamiltonian, the Davis generator can be efficiently implemented on the quantum computer. And also, the special gap is almost equivalent to the mixing time. Okay. Okay. So now I will give a quick introduction for 2D Toric code, the Davis generator, and the special gap. The 2D Toric code is a local commuting frustration-free Hamiltonian. In the Hamiltonian, there are two classes of terms: the star X check and the Plateau Z check. In the star X check, each term is a 4 local, contains the 4 X operators acting on 4 qubits in a star shape. Okay, and in the Plateau Z check, each term is also 4 local, contains the 4 Z operators acting on 4 qubits in a plateau shape. So once the 2D Toric code has length capital L, the total number of qubits is 2L squared. We also assume periodic boundary conditions for this 2D Toric code. Then our goal is to prepare the low temperature thermal state for the 2D Toric code, and we assume beta is very large. Okay. So in this talk, we focus on using the Davis generator to prepare the low temperature thermostat of 2D Toric code. In this Davis generator, this SA omega is a jump operator, help us to transit the eigenvector psi j to psi I. And this gamma omega is a function to help us correct the transition so that we can satisfy the quantum detail balance condition. And here we assume the set of coefficient operator to be the set of all local polys. So this can ensure that the thermostat is a unique fixed point of the Lindblad dynamics. Basically, this ensures when you let t go to infinity, my rho t always converges to the thermostat. And the question is how fast it converges. Okay. So we can show that the Davis generator satisfied something called the GNS detail balance condition. Basically, this means we consider the Davis generator acting on the observable space. This is a self-adjoint operator on the GNS inner product. This is a definition for this is one definition for the GNS detail balance condition. Okay. So since this is a self-adjoint operator, we can calculate its eigenvalue. We can show that all of its eigenvalues is real and non-negative. Then we define the special gap of the Davis generator as lambda 0 minus lambda 1. So the special gap can help us characterize the convergence speed of the Lindblad dynamics. Okay. Good. So now.
Ground state, right?
Yeah.
But then isn't this, you guys wrote another paper which is like ground state preparation, right?
Yeah.
Why don't you just use that instead of push it back to the thermostat?
Oh no, so push back to the ground state is not our ultimate goal. So it might happen that you can push back to the ground state, but the logic information still changes. So you want to push back to the ground state and keep the logic information. This part, in fact, is non-trivial. You will see some example later.
Right. But okay. Yeah. But what are you gonna, the extra part you're gonna talk about can also combine with your ground state preparation work as well, right?
Yeah, I think so. Yeah, I think so.
Okay.
Actually, we don't know whether that algorithm works.
Yeah, so
and there's also a technical problem related to Zhiyan's open question yesterday, which is just we don't have many tools to show the convergence of that ground state preparation.
Yes.
But at least when you talk about quantum temperature, there is a non-singular environment.
So I didn't follow what allowed you to calculate the spectrum. Is it a specific form for the Davis generator? Can you do it for any Davis generator? Or?
No. So for any Davis generator, you mean consider the special gap of the Davis generator for general Hamiltonian?
Yeah.
This is super hard.
So what's the property that you're using?
So we need to strongly use the structure of 2D Toric code. I will also talk a little about this in the later part of the talk. Okay, so now I will talk about the main result. So we are definitely not the first one studying the 2D Toric code. In fact, in 2009, Aliki et al. Also studied the special gap of the local of the Davis generator for 2D Toric code, and they show that the special gap of the local Davis generator can be lower bound by exponential minus beta. So the important thing is that this lower bound is independent of system size. This is the advantage. The disadvantage is when you let beta go to infinity, this the special gap goes to 0 exponentially fast. Okay, basically this means we don't have fast low temperature thermalization. Okay, and furthermore, according to some empirical study and the energy barrier argument, we are almost sure that this lower bound is sharp, meaning that this special gap decays exponentially in beta. Okay, So now a natural question to ask is, can we modify the local Davis generator so that the gap is independent of beta? And the answer is yes. We basically propose a new Davis generator such that the special gap can be lower bounded by the max of exponential minus beta and poly 1 over n. How to understand this result? Basically, 1 beta is a small, this special gap is still independent of beta. And when you let beta to be very large, go to infinity, this special gap is 1 over poly n. So we have poly n decaying special gap. Okay. So the constructions of the new Davis generators is very simple. We still have the local Davis generator where the set of coupling operators equals to the set of the local polys. Okay. And based on the local Davis generator, we need to add some global Davis generator, which highly depend on the structure of 2D Toric code. Specifically, in our global Davis generator, we need to add 4 jump operators. And the coupling operator is a set of local, so the coupling operator is the logic X and the logic Z for the 2D Toric code. So all the logic X and the logic Z are global operators. For example, the logic X are the X operators acting on all the qubits along the origin line. Okay, so all the logical qubits are global operators. Now, then in our paper, we can prove that for this new Davis generator, the special gap can be lower bounded by the max exponential minus beta and the poly 1 over n. So basically, this is our main result. Okay.
So, I mean, if I want to generalize this to 4D, I mean, by adding more logical operators, can I do that? Or?
Yeah, that's a very good question. Intuitively, we believe we can do it, but the most difficult technical problem is to study the mixing time of 4D Toric code. You finally need to study the mixing time of 2D icing with global dynamics, something like this. And that's super hard classically. So I think even when in the classical community, people don't know how to show the 1 over poly n special gap. And that's the main technical difficulty part.
Going back to your original motivation, if you're adding logical X's and Z's, aren't you depolarizing your logical information in the encoded subspace?
What does that mean? Like,
so you had this picture where you're encoding in the ground space of the Toric code, and if you only have local excitation in local, that doesn't mix up your logical states.
Oh, yeah. So. Right. So under this picture, our goal is not to preserve the logical information. You are right. So the reason we add this global operator is to break the logical information so that we can mix, so we can summarize fast. Yeah. So I think in the later part of my talk, I will talk more details about how to preserving the logic information.
Related to my earlier question, if you really want to just to passive memory, then you shouldn't add this logical. Right.
So I will discuss more about this later. So you will see it. Okay. So yeah, the implications of our result. So first implications is the polynomial mixing. Basically, for our new Davis generator, we prove that the special gap can be lower bounded by the max of exponential minus beta and poly 1 over n. This essentially gives us an upper bound for the mixing time. We can prove that the mixing time can be upper bounded by beta times poly n log 1 over epsilon. Here, the linear beta dependence mainly comes from the singularity in the chi-square divergence. So when you let beta go to infinity, the thermal state will converge to the ground state, which is a singular state in the chi-square divergence. And this will cause the blow up of the chi-square divergence, finally give us the linear beta dependence in the mixing time. Okay. Yeah. One remark is in a recent work by and Zhiyan in the audience, they basically provide an algorithm to prepare the thermal state of for 2D Toric code in order n square time from maximum the mixed state. And I think Zhiyan will give a detailed talk about this on Thursday. Okay. Yeah. So in the second implications of our result is in our work we also show that in fact the ground state is easy for the local Davis generator. Okay. So how to understand this result? First, for 2D Toric code, we can first do the Hilbert space decomposition. We can decompose the original Hilbert space as a C4 tensor product with a C2 to the power m minus 2. Basically, we can rewrite it as the direct sum of C1 to C4. And each Ci is called the syndrome space. For each syndrome space, it only contains one ground state and excited state with the same logic information. Okay, basically you pick any vector inside this syndrome space and you measure. So you measure it with the logic operators. The output is always the same. Okay, so now to understand the thermalization for 2D Toric code, there are two parts of thermalization. The first part is you need to thermalize across the syndrome space. Essentially, what you do is you assign equal weight across the syndrome space. Then in the second part, you need to thermalize inside the syndrome space. Basically, what you do is you assign different weight to different eigenvectors according to their energy. Okay, and we can show that for the local Davis generator, the thermalization in the first part is very hard. Basically, you need to overcome the energy barrier in the first part. This is where exponential minus beta is come from. Okay. However, the second part is very easy. So in our work, we can show that if you restricted ourselves to the syndrome space, then the special gap of the local Davis generator can be lower bounded by max exponential minus beta and the poly 1 over n. Basically, if you only consider the syndrome space, the low temperature mixing of the local Davis generators can be very fast even under low temperature. Okay, this is also an example of the folklore belief mixing is easy within a phase. Okay. Yeah, and the one quick remark is the ground state for 2D Toric code is known to be easy because of quantum error correction. Okay, yeah. Now I can talk about my last implication, which is about the quantum memory. Basically, in the second implication, I tell you that if we restricted ourselves to the syndrome space, then the low temperature thermalization of local Davis generators can be easy. Okay, and we also recall that the fast low temperature mixing might be helpful for passively protected quantum memory. Then a natural question to ask is, we consider the Davis generator and we consider the local Davis generator set beta equal to infinity. Is this a good candidate for passively protected quantum memory? So basically what we do is we choose the protector to be the local Davis generator, set it to be beta equal to infinity. And we want to show that the logical information can be almost preserved along the whole dynamics. The intuition is still the local Davis generator will quickly kill the excitation and preserve the energy. Okay. However, the answer is negative or not necessary. Why? We can think about the 1D icing case. So here we start from the ground state of 1D icing, and we encode the logic information in the first qubit. So basically, we assume we take the ground state with all up and encode the logic information in the first qubit. Then in the first step, we apply the noise. We apply the noise operator. We assume it flips the second qubit. Next, we apply the protection operator. In the ideal case, it will flip the second qubit back. So we go back to the ground state and keep the logic information. This is a good case. Okay. However, in the 1D case and in the 1D IC model, we do have a bad case. So the protection operator might flip the third qubit, then the fourth qubit, and finally the first qubit. Along this way, we can still go back to the ground state space, and the logical information get changes. The reason we can go this way is if you take a look at these three vectors, so the energies of these three vectors are the same. Basically, if we move this way, there is no energy penalty. Okay. We can also look at this phenomenon in the energy picture. In our new dynamics, after rho zero get excited, the Davis generator might quickly drive it back to the ground state. However, it might also take another way and go to another ground state, and the logical information get changes. In this movement, we don't have any energy penalty, and by some random walk argument, we can show that the probability this happen is at least poly 1/n. Okay, so we don't have passively protected quantum memory. In the case of 2D icing, the situation is very different. Here, you can imagine that the center qubit get flipped. Okay, then now if we apply the protection operator, the only way to go is to flip it back. All the other ways will have for some energy penalty and will happen with very low probability. Okay, so unfortunately, in terms of quantum memory, 2D Toric code is more like a 1D icing. So although we can show the faster low temperature mixing inside the syndrome space, we still don't have good passively protected quantum memory. Okay. So finally, conclusion. In this talk, I provide a new Davis generator, which can ensure polynomial low temperature normalization from any initial state. We also show that for the local Davis generator, if you restricted ourselves in the syndrome space, we can guarantee faster to low temperature normalization or faster mixing to the ground state. Finally, we also discuss the passively protected quantum memory, and we show that there are still some gaps between faster low temperature mixing and the passive quantum memory protection. Okay, and any question?
The problem that the local doesn't work is because it has all the same energy, right? You can move around.
Yeah.
But what if you like make it a little bit inhomogeneous? Just change the coefficient of the couplings a bit.
You mean change the coupling in which change which
bit of the nearby side?
Yeah, but you still have the same problem. Yeah. So for example, in the 1D icing, even you changes their coefficient.
Yeah, I make the J to be J depend on the side. The J.
Yeah. So
that would still be the case.
And so in that case, I see what you mean. But in that case, it will also depend on which bit you get flipped. I think it's kind of. I think for me, it's not very clear up to now. But this might be interesting to see.
So there is a way to counter this propagation, the effectively zero energy propagation, by introducing tension operators, loop tension operators, which effectively because in the physical picture, what's happening is that the excitation is translating on the axis, right?
Yeah.
And you want to suppress that.
Yeah.
And so you can introduce effectively zero energy transitions induced by the bath to create tension in the strings.
Okay.
And that will prevent this this translation or suppress this translation.
I see. But after adding this, can you still guarantee you can faster go to the ground state?
So the ground state transition is induced by the local by the x and y terms.
Yeah.
But the string tension is what the additional term adds.
Okay, I see.
Yeah, I think we can discuss more about it.
Sure. Yeah. I can tell you.
Yeah. Thank you.
Actually, maybe can I? So
I think if I understand correctly, are you thinking about like Z operators for the string tension for 1D?
In the Toric code?
Well, because in the Toric code, I think you can't measure the string tension because that would kind of violate the fact that these logical operators are invisible. So like, a logical operator is something that causes zero energy, but involves applying, a loop that crosses the entire system. Yeah. So if you have a local Hamiltonian, I don't think you can also have a local operator that kind of measures the tension of this loop linearly in system space.
Measured or just suppress it growing?
Like at some level, this string operator has to be invariant on the ground state for you to have like an error correcting code. Yeah. Like it's almost like related to the error correcting conditions itself, There's no local Hamiltonian that can distinguish between the different phases.
question over there.
Okay. So you said earlier that 2D Toric code is equivalent to 4D easing at some point, or some other model equivalent to 4D or like higher dimensional easing.
Oh yes, yeah. So my argument is like this. So basically, if you want to study the missing time or the spatial gap of a Davis generator to 4D Toric code, then you so by some Hilbert space decomposition argument, you essentially reduce the 4D Toric code to 2D icing model and within a phase. Yeah.
So so I know that like for easing model on higher dimension, like 3D or something, there's a phase transition. Oh, actually 2D, that's the phase transition. So Glauber will be slow mixing at some low temperature. Does that imply anything?
Yeah, so that's also a very good question. But to my knowledge, the phase transition argument only tell you that if you want to get a global low temperature thermalization, it's very hard. But if you restrict yourself to a phase, I think we don't have a very rigorous lower bound. Like tell you this is hard.
So I think actually in this morning there's a short example when even when you restrict to one phase in like say 3D easing, you still slow mixing.
Yeah, you're right. So in fact, in that talk, I also asked this question. I think he provided an example for 3D, but not 2D. So I think there is no known result for 2D. So we still have some hope, but I'm not sure. Yeah.
Yeah. So maybe following upon this line of thought, so can we understand your result as like saying that like something like Swenderson 1 is efficient in 1D easing? Because you're adding like global jumps, right? So
yeah, I think it's hard to say that. I think so the main application of Swiss and 1 is in the 2D icing, right? And I think the reason it can be efficient is not only it can add a global jump, but it can also make like the thermalization within a phase to be very efficient. So I think there is more in the Swiss and 1.
It's kind of jump over the syndrome subspaces using the language here in correction code. Right? It's like positive and the negative phase. You flip it directly.
Yeah.
More detailed.
Yeah.
Chop out like some local block and then flip instead of global.
Yeah, of course, it's in the space. It's not in the Hilbert space decomposition.
Yeah. Yeah.
Questions?
So I guess one question is like, can you use this type of formalism to like kind of try and learn about the physics of some of these like new fancy LDPC codes that people have been constructing? Because I think like the Toric code has been very well studied, which is a great place to start developing these tools. But then can you also start to like apply some of them to some of these models that we don't have good physical ways of thinking about?
Yeah, so
describing what kind of interesting questions. Like,
So like, for example, if you now have like an LDPC code defined on expander graph, can that give you like a passive memory of the same form that you described here? You know, so like Toric code maybe doesn't work, but then if you describe something like a Toric code in an expander graph, then like would it start to work now? You know, these types of questions.
Andy Lucas has a recent paper talking about exactly that.
I see.
But the argument is not like proving end-to-end to prove a spectral gap. There are some arguments why LDPC is good.
I see. Could you use these tools to like formalize rigorously these arguments?
Yeah, I think currently we are still look at this because it's a really recent paper.
Yeah. Okay.
But I do think this is a very interesting and valid question. Yeah.
Cool. Thank you.
Thank you.
So if there are no more questions, let's thank Zhiyan again. There'll be a small break and we'll reconvene at 2:30.
Whether